has made important contributions in Ginzburg-Landau theory, fluid mechanics, fluid structure interaction. And today he's speaking about free boundary Navier-Stokes. So Ian, if you can re-share your slides.
Certainly, 1 second. All good, can you see?
Yes, looks good. So yeah, floor is yours.
Great, thank you very much for the invitation. Thanks a lot, Jan and Stanley. It's a pleasure to be speaking to all of you in this format. We were just saying before the waiting room was emptied that one of the silver linings of the pandemic is that we get to interact with each other in this new way across the entire world. So it's really exciting to me to get to talk to people all over the world, from the safety of my basement here in Pittsburgh, Pennsylvania. Let me also mention from the top here that everything I talk about today is joint work with my colleague Giovanni Leoni, who's also at Carnegie Mellon. I'm gonna, as the title suggests, I'm gonna be talking about traveling wave solutions to the Navi-Stokes equations. Before I get to the traveling wave part of this, I want to sort of give you a general overview of the incompressible Navi-Stokes problem in the context of, in the context of free boundaries. So many of you will have seen this before, but we will rapidly move away from this. For those of you who are not experts in free boundaries, this will set up the framework for the problem. We're going to be entirely concerned with layers of incompressible fluid in this talk, and always viscous fluids. The fluid will occupy an unknown and dynamic domain. So we will denote that as omega of t. So the domain in which the fluid lives is going to change in time. This will be a slab-like domain in Rn, where n is between 2 and 3. Or is either 2 or 3. In fact, actually, this description works in arbitrary dimension, but of course, the physically relevant dimensions are 2 and 3. So the reason we call this a slab-like domain is because it is a domain like in this this cartoon here, where there is a horizontal cross-section that runs across the bottom of the fluid that is really just a copy of Rn minus 1. So it's completely flat. There's no topography in the bottom of the fluid here. And we will think of the fluid itself as when it's at equilibrium, meaning when everything is quiescent and unmoving, we'll think about it as being just a completely boring layer of depth b. We will fix the coordinate system in such a way that the vertical variable goes between 0 at the bottom of the fluid, and that the equilibrium depth is this number b up here that I've drawn like this. And then the free surface will be a perturbation of this equilibrium depth parameter b. And we will model this in the simplest possible way as a free surface that is given as the graph of a function. So this will not allow for sort of complicated structures like waves that are turning over. This will be the simplest configuration where we can describe the free surface as the graph of a function zeta. So zeta will be a function of the horizontal variable. When I write x prime, that always means the first n-1 components of x. And it will be changing in time. So it's also a function of time. So then the upper free surface then is the set of points where the vertical variable is b plus zeta of x prime comma t. And then our fluid domain can be specified as just a collection of points lying between the upper free surface and the fixed lower surface. So again, the dynamic part of the problem is the unknown free surface. The bottom is completely fixed. You can think about this as a sort of very simplified model of an ocean. So let me tell you some of the modeling assumptions here. We're going to assume that the fluid is incompressible and viscous. And in order to describe the dynamics of it, then for each time, I need to know the free surface function, which I just told you about. And this is a function defined on the cross section. We also need to know the fluid velocity, which I will call W for the moment. And we also need to know, which is a vector in Rn. And we need to know the fluid pressure, which is a scalar, and I'll call it capital P for the moment. And the key point about the velocity and the pressure is that they are actually defined in the moving domains, omega of t here. So they're not defined in full space, they're defined in a domain that is changing in time. So we also need to specify the various forces that will act on the fluid. We're going to assume that there's a constant gravitational field modeled by the vector field minus rho times a constant g, like a gravitational constant En, where En is just the standard unit vector pointing up. So that means that gravity points down, gravity points down in the direction of the flat bottom. We'll assume that above the fluid is a sort of constant external pressure that I'll call P external. This won't play much of a role, so you can forget about this very rapidly. The most important of the forcing terms here is that we're going to assume that there is an externally applied surface stress, which we will model as a tensorial valued map. So the external stress is going to take values, and so I'll write it as n by n symmetric, but it's really a symmetric tensor. And we will think of it as being actually not defined in the bulk of the fluid, but on the free surface. So this is some sort of stress that is being applied externally from, let's say, external sources to the fluid, or on the fluid rather. And the other thing that we will account for is that on the free surface, we will allow for the effect of surface tension, which is usually modeled by a non-negative parameter sigma called the coefficient of surface tension times the mean curvature operator, which we'll write as h here. And when we're in the simple situation where the free surface is given as the graph of a function zeta, the mean curvature operator can be written as a sort of nonlinear version of the Laplace operator, or if you prefer, this is the first variation of the area functional associated with the graph zeta here. Okay, so this is some sort of force that is well, meant to model surface tension due to molecular forces on the free interface. So this is a complicated system. So the first thing we're going to do is get rid of a bunch of the parameters. So by sort of rescaling the problem, I can assume without loss of generality that the viscosity is 1, the density is 1, and the gravitational constant g are 1. It is 1 rather. So putting together the Navier-Stokes system, we then have the following dynamic equations of motion. So within omega of t, we have the standard incompressible Navier-Stokes system. So this first equation is the sort of balance of momentum that is analogous to Newton's second law. It's essentially telling us that the force acting on the fluid, which in this case is just the gravitational force, is going to be balanced by the mass times the acceleration that the fluid feels. And I'm sorry, actually, these are also forces that are felt on the fluid. So this is the acceleration term. The second condition here, which is known as the incompressibility condition, is really a balance, or sorry, not balance, conservation of mass. It says that mass is locally preserved along the flow. The third and fourth equations are equations that hold on the free interface. These are sort of boundary conditions that you have to specify in order to close the system. The first is what's called the dynamic boundary condition. It's kind of analogous to Newton's third law. It's a sort of force balance that is occurring on the free interface. And what it tells us is that this object called the viscous stress tensor, which is the pressure times the identity minus the so-called symmetrized gradient. So this funny math BB dW stands for the derivative of W plus its own transpose. So this thing has to be, this is a tensor, it then hits the outward pointing unit normal mu, and this vector then is balanced by the sum of the mean curvature term, which I described previously, and the sources of external force. And those sources are the external pressure, which is just a constant, and this external stress term. So this is really the crucial feature here. This is how the externally applied force stress and pressure sort of act to drive the fluid through this equation on the boundary. The final equation on the upper free surface is what's called the kinematic boundary condition, and it's not a force balance one, but rather one that is just sort of tracking the evolution of the free interface, and it tells us that the time derivative of the graph function that determines the free interface is proportional to the normal component of the velocity field, and there's a proportionality constant that comes from the geometric, the area form associated with the free surface. And finally, we will impose the so-called no-slip condition on the bottom of the fluid. This is a standard modeling assumption when we're working with viscous fluids. It means essentially that fluid particles will stay pinned to the bottom of the fluid. One thing that I want to point out is we can write things in a concise way by using this stress tensor. So I'll call this stress tensor that I underline here S. And a nice computation shows that the divergence of S can be written as the gradient of the pressure minus the Laplacian of W minus the gradient of the divergence of W. And since I'm working with divergence-free vector fields, then I can rewrite this term here as the divergence of S. So this is convenient in terms of writing things in a concise way. Okay, so this is not a talk about fully dynamic Navier-Stokes. It's a talk about traveling wave Navier-Stokes. So let's introduce that ansatz. We're going to assume that the stress that is applied, the external stress tensor T external, is stationary, and by that what I mean is just time independent when we view it in a coordinate system that is moving along in a manner that is parallel to the bottom and moving with velocity gamma times E1. So gamma is the sort of traveling wave speed, and we can assume without loss of generality that the traveling wave direction is E1, because we can always rotate our coordinate system if necessary so that the source of external stress is moving in that direction. And you can think about this as a model of a source of stress that's sort of translating uniformly above the fluid. Sort of my favorite model of this is to think about a tube of air that's sort of being held above the fluid and translated along. But you can think about this in many other contexts. For instance, as a very simple model of wind, or you could think about this as modeling a small ship that is sitting on the surface of the fluid and zipping along, or your favorite variant of these things. Now, the way that we'll actually manifest this mathematically is we're going to assume that this external stress, which is a priori a function of space and time, is actually just a fixed function defined only on the cross section. So this is for simplicity in this talk. And we will plug in the variables x prime, which is just the horizontal variable, minus gamma T1. So it's just a fixed profile translating in the E1 direction at speed gamma. And once we've made this ansatz, we will also assume that the free surface function is in traveling wave form. So the new traveling wave profile will be the function eta. The traveling wave profile for the velocity field will be a function v. And the traveling wave profile for the pressure is going to be slightly different from these, in addition to making the traveling wave ansatz, as I've done here. So the traveling wave profile will be q, but we're also going to subtract off the hydrostatic pressure. And this is done for convenience to get rid of this external pressure term. If we do this, then we rephrase the entire problem in a stationary fluid domain, which still has an unknown free surface. So we still don't know the domain omega, the free surface function eta, and so this is still a free boundary problem. So the problem is now posed not in a time-dependent domain per se, but rather an unknown domain, omega b plus eta. So here's a little cartoon of this to make it a little more concise. The idea basically is that, we have this tube that's blowing air on the fluid, and this thing is sort of translating along. And the hope then is that we can find a profile for the domain and a pressure Q and a velocity V, such that when we view this in this sort of translating coordinate system, we find something that's actually time independent, that is actually a stationary problem. Okay. So when I make the traveling wave ansatz, I of course shift to a problem that's time independent, which I've written here. This is what we'll call the traveling wave system with traveling wave speed gamma. So it's exactly the same system I wrote before. It's just that everywhere where previously I had a time derivative, I replace it with a spatial derivative in the E1 direction multiplied by gamma. So this is really exactly the same system we saw, just time derivatives have become derivatives in the E1 direction. I've also unnormalized things by getting rid of the unit normal and replacing them by the non-unit normal, which I've just done for convenience so that it's easier to see the linearized structure underlying this problem. So the non-unit normal can be computed in terms of the free surface function in the obvious way. Okay, so we have this system of equations. an initial thing that we can ask for is if there are very, very simple solutions to this, and of course they are. They correspond to sort of trivial quiescent solutions. So for any traveling speed gamma, so this is the wave speed, if I have zero external stress, then I can get a solution just by assuming that there's no velocity, the pressure is zero, and the free surface is zero. So forcing the pressure to be zero here is one of the reasons that we subtracted off the hydrostatic pressure earlier. It's more convenient to work with zero than having the pressure be hydrostatic. Oh, well, I should also mention that one of the other consequences of sort of normalizing by subtracting off the hydrostatic pressure is that the gravitational forcing term has shifted from the bulk, where it used to be the vector En. It is now, it's given rise to this term on the boundary, which is just a multiplicative factor times the free surface function eta. So essentially, if I had not normalized gravity to be 1, gravity would be multiplying this term here. Okay, so the point is that, you know, we have this collection, this one parameter family of incredibly boring solutions to this problem. In fact, you can ask, well, you know, is this sort of necessary? And the answer is yes, in some sense. So if I posit that I have solutions to this system that lie in some standard Sobolev space, and I won't tell you precisely what it is, but let's say something like H2 for the velocity field. Then for any velocity gamma, if I assume that t is equal to 0, then I can do a simple sort of energy type estimate and actually deduce that V is equal to 0, Q is equal to 0, and eta is equal to 0. And of course, this is not surprising because the Navier-Stokes system is dissipative. And so if I'm going to expect there to exist a traveling wave solution, you expect there to have to be some sort of source of power, some sort of source of stress that is applying a power, providing power to the system so that the dissipation can sort of constantly remove that power in a sort of balanced way. Okay, and so what I'm saying here is if you don't provide a source of external stress, well, then dissipation just is going to kick in and force the solution to be trivial. Okay, rephrasing one more time, it means that if I hope to find a traveling wave solution, I have to have some sort of external source of stress or force. Okay, this is not the case without viscosity. So if you have an inviscid fluid, you don't have to have this sort of forcing. And so you can look for sort of free solutions. And there is an incredibly huge literature devoted to this that goes back almost 200 years. 150 years at the very least. And so I will not attempt to survey this in its entirety, but let me just say that for the inviscid problem, the initial work was almost all in 2 dimensions and concerned irrotational fluids where the vorticity is set to be 0. And over the course of something like 75 years, analysis progressed until the point where we had a proof of the Stokes conjecture in the 1980s. This constructed traveling wave solutions to the Euler system with sort of the sort of maximally steep waves. Or waves of maximal opening at the crest. More recent work in the last only 20 years or so has opened the problem up to the rotational setting. This is mostly flowing from the work of Constantine and Strauss and the collaborators and students. More recent work has allowed also the analysis of problems in 2 dimensions with applied forces that are meant to model wind or surface forces, notably the work of Miles Wheeler and Sam Walsh and his collaborators. Comparatively, there's much less known in the 3D case. Everything I know of is actually known only in 3D for irrotational problems. If I were to then talk about what's known in the viscous problem, the answer is very, very little. There is a little bit of work for the case when gamma is equal to 0, namely these are not traveling wave solutions, but actually just stationary solutions with forcing in geometries that are close to the slab-like geometries that I'm describing, but not identically equal to them. So it's not exactly the scenario that I'm working in. One of the things that I really want to mention here is when gamma is not equal to 0, there's some very nice experimental work that I am aware of, where they actually do in a wave tank an experiment that corresponds to the picture I showed earlier. So they actually they put a tube on a wave tank and they blow air onto the surface of the fluid, and then they move the tube uniformly, and they mount a camera in the system and take pictures of the system, and they find that in certain parameter regimes, they can actually cook up traveling waves or things that look very close to being traveling waves. So actually, this experimental work was in some sense actually inspiration for this analysis work. These things are actually observed in experiments. However, to the best of my knowledge, there were no actual analysis results for viscous traveling waves prior to this work with Leone. So here is a imprecise version of the theorem, only in a special case. So again, this is work with my colleague Giovanni Leone. The result says that if we're in dimension 2, then we can allow surface tension to either be turned on by having sigma positive, or we can turn it off by allowing sigma to be 0. But if we're in dimension 3 or higher, actually, sorry, just dimension 3 for the purposes of this, then actually we need positive surface tension. We can't get away with no surface tension. We then need a regularity parameter that's supercritical. It needs to be bigger than n/2. And then what we can say is that there exists an open set WS contained in the space r minus the origin. So this is where the wave speed is going to live. And this is the standard Sobolev space HS plus a half. This is where the applied stress T is going to live. So there's an open set in this space of wave speed crossed with applied stress. And there exists a Sobolev type Banach space XS, and I'm not going to tell you precisely what it is at the moment, such that the following hold. So the first is that our previously identified curve of trivial solutions sits inside WS. So this is a pretty big set in some sense. It contains all values, all non-zero values of gamma crossed with 0. So it goes all the way out and contains all possible wave speeds. The second thing is, even though I'm not going to tell you what the space XS is precisely, what I can tell you is it has supercritical embedding type properties. So if this XS is where the solution triple is going to live. So if you give me a velocity, a pressure, and a free surface that live in this space XS, then in fact, I can tell you that the velocity is classically differentiable up to order 2, and the derivatives up to order 2 are bounded. The velocity is classically differentiable up to order 1 with bounded derivatives, and the free surface function is classically differentiable at least up to order 3, and all derivatives are bounded and go to 0 out at infinity. Okay, so there's a nice container space that we find here. And moreover, the real meat of the theorem here is this third bullet point that says that for every pair of traveling wave speed and applied stress T sitting inside this open set, there exists a traveling wave solution triple, VQ eta, living in this new Banach space that solve our traveling wave equations classically. These things are locally unique, and they will obey various auxiliary estimates that are convenient for the problem. So for instance, we have nice control on the magnitude of the free surface function, which guarantees, for instance, that the set omega is open, things like that. And moreover, we can guarantee that the map that takes the traveling wave velocity and the external stress to the solution is locally Lipschitz. Okay. Now, of course, if you see this statement, you can probably guess how we prove something like this. This thing smells of the implicit function theorem, and of course, that's how we're going to do something like this. Before I tell you about this, let me give you some remarks. So our solutions have the free surface decaying to 0 at infinity. So in the language of the free boundary fluids world, this is what is typically called solitary waves. So our perturbation sort of lives locally in space and sort of decays off to 0 at infinity. So the reason I'm not telling you the precise structure of the space XS is because it involves new, previously unstudied Sobolev type spaces with very odd properties. And I'll get to these later, I hope. But this is not a vanilla Sobolev space that we're working in here. We had to actually invent some new Sobolev spaces to build these solutions. The other curious thing about our result is it works for arbitrary wave speed except for zero. So we can actually produce solutions with that are traveling at extremely fast speeds, but we cannot say anything at all about the actual stationary problem when the solution is not moving at all. And the reason for this is that the parameter, the non-vanishing of the wave speed actually is going to play an essential role in determining the topology of this Banach space. And if you turn this wave speed to zero, there's going to be a significant topology change and we will not be able to actually construct our solutions. So this is really a talk about traveling wave solutions that can say nothing about stationary solutions, weirdly enough. The other thing I want to mention is the theorem that I'm giving you is a simplified version that is meant just for expository purposes in this talk. In the real paper, we allow more general settings where we have external forces that act in the bulk, and we also include sources of external stress that are more complicated than what I'm talking about now. They're functions also of the vertical variable. Also, the result in the paper actually works in any dimension bigger than or equal to 2. So if for some reason you like fluids in 4 dimensions, our paper's got you covered. And the other thing I want to mention is in recent work with a student of mine, Noah Stevenson, we have extended these results to handle the case of multi-layer fluids. So we can now handle the case of layers of stacked fluids and produce solutions in that context as well. Okay, so I want to spend the rest of the talk sort of giving an overview of how we go about proving this result. As I said, it's clearly going to be an application of the implicit function theorem. The very first step, as in most free boundary problems, is to rephrase the problem in a domain that's actually not changing. And this is so that we can bring to bear the standard PDE techniques on moving domains. And so the way that we're going to do this is by actually just flattening the unknown domain into the equilibrium domain, which I will just write as omega instead of omega b. And this is just the collection of points for which the vertical variable lies between 0 and b. And the way that we're going to do this is in the simplest possible way. We're going to do absolutely nothing in the horizontal direction. So our flattening map is going to be the identity in the horizontal directions. And over each vertical fiber, we're just going to make a linear distortion of the interval 0 to b to the interval 0 to b plus eta. And you just do this in the obvious way by making a linear map that maps one interval to the other. So this function is particularly nice because what it means is that our change of variables map is going to inherit the regularity of the free surface function in a very simple way. You can basically read off the properties of this change of variables map by understanding the properties of the free surface function. Once we have this flattening map, what we're going to do is rephrase the problem in the equilibrium domain. So we're going to pull everything back into the equilibrium domain by using this map F. And we will then define the new unknowns U for the velocity field and P for the pressure field, just via composition with the flattening map. Now, unfortunately, when you do this, you get the benefit of writing the problem in a fixed coordinate system. Unfortunately, what you arrive at is an elliptic problem that is an absolute mess. It doesn't look that bad the way that I've written it here, but this is actually, if you stare at it for a few minutes, it's now a quasi-linear version of the problem that we saw before. The reason it's quasi-linear is because everywhere where I previously had just a simple partial derivative, I have to now replace it with essentially A times the gradient, where this matrix A is the inverse transpose of the derivative map associated to this flattening. So this involves derivatives of the free surface function eta, and so you can, by staring at this for a while, you see that this is actually quasi-linear now. This is a general feature of essentially all free boundary problems. Even if they look linear in the moving domain, when you pull them back into a fixed coordinate system, they become quasi-linear due to this sort of change of variables. So basically, that's what I mean when I write grad A, div A, Laplace A. So these are basically what you get when you replace the Laplacian, the divergence, and the gradient with these versions of the operators. So we write it in this form, and the price that we pay is we now have a significantly uglier set of equations that we call the flattened traveling wave systems, wave system. Now, As I said, our strategy is to use the implicit function theorem. So the first thing that we're going to do is linearize this around our trivial solutions. So what we're going to do is linearize around arbitrary gamma, t equals 0, u equals 0, p equals 0, and eta is equals 0. And the underlying linearized system then becomes the key thing that we need to understand if we're going to use the implicit function theorem. When we do this, we end up with this system here. And I have included data on the right-hand side just because we're going to need to show that this system is uniquely solvable for all such data. So it's important to include it in this setup here. So this problem we call the traveling gravity capillary Stokes problem, because if you stare at this for a moment, this is basically, these two equations are basically a Stokes system, and we have some sort of combination of capillary operators and sort of traveling wave form boundary conditions. Okay, so this is what we need to attack. We need to establish that this linearized problem induces an isomorphism in order to apply the implicit function theorem. So if you're like me, if you see something like this and you think a little bit naively about the physics of the problem, you think, well, the nice thing to do here would be to treat this problem initially with gamma is equal to 0. You know, maybe the solutions that we're gonna construct are only going to be valid for extremely slow traveling speeds, and we can construct them as perturbations of the problem where gamma is equal to 0. So this is, of course, what Giovanni and I first did. And another benefit of this strategy, which I personally found incredibly compelling, was that if you attack this linear problem with gamma is equal to 0, there's a beautiful decoupling that happens, where the problem can be decoupled as a first problem that involves only u and p and some of the data. And once you have solved for u and p, you can then think about taking it together with the remaining bit of data, k sub n, the nth component of this vector field k, and then solving an elliptic problem for eta in order to finally solve for eta. So it has this beautiful sort of like multi-tiered structure where you can sort of solve first for u and p and then finally for eta. So this was our initial strategy for attacking this problem, namely to focus on the case where gamma is equal to 0. Unfortunately, this problem runs into a fatal issue. And the issue is one that should be familiar to anyone who's studied the Stokes problem before. And the problem is that if I look at this first elliptic problem up here, what has happened is by isolating only the first n-1 components of the applied stress condition, I have lost a boundary condition for the pressure. And the practical implication of that is that in this first system, the type of elliptic estimates that I will be able to get will only allow me to get estimates for the gradient of the pressure, not the pressure itself. So for instance, if we have the usual elliptic scaling for the Stokes system where I have a velocity estimate, let's say in the space hs plus 2, then rather than getting an estimate for p in hs plus 1, what I'll get is an estimate for the gradient of p in hs. Now this may seem like it's perfectly harmless, except now you need to look at this second equation where what it's saying is I need to evaluate the trace of the pressure onto the upper free surface and then invert an elliptic operator with this as the data on the right-hand side. So this begs the question, what can we actually say about the right-hand side of this PDE here? Because we don't know that the pressure is going to be in a standard Sobolev space. In fact, all we know is that the pressure is in a homogeneous Sobolev space, namely that, you know, we know that the gradient is in L2, and okay, we also have control of higher order derivatives, but at a fundamental level, what we know is that the pressure is in the space H1 dot. So this begs the question, well, okay, so what do we actually know? What is the trace space associated with H1 dot? Weirdly enough, this was an open question. This was not something that we were able to find in the literature. So Giovanni and I first attacked this problem. And what we unfortunately found is that the trace space associated with H1 dot is a non-standard fractional homogeneous Sobolev space. So it's a weird new type of homogeneous Sobolev space. And unfortunately, if you use that space in this problem and use this to invert and solve for eta, then in fact, the estimates that you will get are not good enough to show that eta is bounded. And in fact, it's significantly worse than that. We're not even able to show that it's a function. What the best that we can get is that it's an equivalence class of tempered distributions modulo polynomials. And obviously this is completely useless from the perspective of attacking this problem, because eta is supposed to be a function whose graph gives me the domain in which I'm working. So I can't afford to have this sort of ambiguity. So this approach just completely fails. Okay, so it fails. What do? Well, we go back and we say, all right, well, what happens if we looked at the case when gamma is not equal to 0? In this situation, unfortunately, this beautiful decoupling that is so compelling when gamma is equal to 0 is not available. So we have to attack the problem more holistically. And so it's not at all clear what happens in this problem if you view it holistically. So our strategy basically was to first see what happens if we just sort of ignore eta. And what I mean by that is basically we're going to imagine that sort of we know eta somehow, and then figure out what's going on in the resulting linear problem for U and P. Now, what happens in this situation is actually we arrive at what we call an overdetermined problem. And the reason it's overdetermined is because basically this Stokes system here comes equipped with the ability to handle in scalar boundary conditions on both the top of the fluid and the bottom of the fluid. And on the bottom, we are using in boundary conditions, but on the top, we're actually imposing n+1 boundary conditions, because there are in conditions imposed here with the applied stress condition. And then there's an extra condition that's imposed by trying to impose the condition on the normal component of the velocity. So this looks problematic, and in fact it is problematic, because if I were to ignore this equation that I've put in a box here, then in fact the resulting elliptic system with just this boundary condition on the top is well posed. And so I can always solve this uniquely for any given k. So in fact, this is something we prove in the paper. In fact, maybe let me not read it too carefully here, but in appropriate function spaces, the corresponding map associated to this PDE here induces an isomorphism. So what that means is that in general, we're not going to be able to solve this problem. If I specify f, g, h, and k arbitrarily, I should not expect a solution to exist. They're going to have to satisfy some special compatibility conditions in order for there to be a solution. So let's try to get our hands on what those compatibility conditions may be. The first of them is going to be familiar to anyone who's worked in viscous or incompressible fluids. If I have the condition that the divergence of U is equal to G, and the normal component of the velocity is h on the top and 0 on the bottom, then I should be able to find a sort of integral relationship between G and H. And if everything were L1, then in fact we could do this. We would integrate G over the domain omega, use the fact that this is equal to the divergence, integrate using the divergence theorem, and use the fact that we know the normal component of the velocity on the top and the bottom to find that the integral of G would have to be equal to the integral of H over the cross section. However, we're going to work in L2 based spaces on a domain omega, which has infinite measure. And so we're not going to ever be able to justify that things are in L1, so these computations aren't valid. So we have to come up with a more sophisticated implementation of these of this compatibility condition. And one can do this. You can play games with test functions. And what you'll find instead of this exact identity is that this function h, which is a function on the cross-section, minus the integral of g over each of the vertical fibers, so this ultimately defines a function only on the cross-section, has to belong to the homogeneous Sola space h dot minus 1. Now, this may seem like it's just completely out of nowhere, but in fact, this is a weak formulation of the condition that we saw above, because I can rewrite the condition that we saw above as the integral of this new function that we're studying down here being equal to 0. And you can think about this as saying that the Fourier transform of this function in a box here vanishes at the origin. This is not equivalent to what we're saying here, but the inclusion in the space h dot minus 1 requires that this function is, for instance, not too big at the origin, or else this integrability condition would not be satisfied. So what we have is a sort of weak L2 version of the L1 version that you would get from the obvious integrating compatibility condition here. Okay, so this establishes one compatibility condition that we're going to need to contend with. It's not the main one though. So to keep pushing in this direction, we can't just do something as simple as integrating by parts anymore. What we have to do instead is we have to take a cue from the closed range theorem and play games with the formal adjoint of our overdetermined problem. And amusingly enough, the formal adjoint of the overdetermined problem is actually an underdetermined problem. It has a similar form, the sign of gamma flips, but otherwise it's a very similar system of PDEs in the bulk. What makes it underdetermined is that rather than specifying in boundary conditions on the free surface, I'm now specifying in -1 boundary conditions. Now, what's interesting about this underdetermined problem is that you can always augment an underdetermined problem with auxiliary conditions. And if I do so, then I can actually turn the underdetermined problem precisely into the applied stress Stokes problem that I mentioned previously. So I can always add the nth component of this boxed equation and just call the resulting function phi. And if I do that, then the solution to this problem will actually be something that I can determine with this isomorphism that I talked about earlier. I can determine the solution as the inverse of this isomorphism acting on the triple 0, 0 phi times En. Okay, so in some sense, I can sort of parameterize the kernel to the underdetermined problem. And if you think about this for a minute, this is exactly the sort of thing that we do when we play games with the closed range theorem. So I can get a second compatibility condition as follows. I will assume that I have a solution UP to the overdetermined problem with data F, G, H, and K. I'll multiply it by something in the kernel of the underdetermined problem, which is the formal adjoint of the overdetermined one, do the usual tricks of integrating by parts, blah, 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 blah. And what I will end up with at the end of the day is a compatibility condition on the data. So the compatibility that we condition that we get is that this sort of integral condition has to hold here, where phi is an arbitrary function in an appropriate regularity class. This is what we're using to parameterize the kernel of the underdetermined problem. And then the resulting V and Q are determined as above via our isomorphism that we produced earlier. So this is the second condition that has to be satisfied in order for a solution to exist. It's a necessary condition. And nicely enough, the two conditions that we found are not only necessary, but sufficient. And so the point is that our problem, our overdetermined problem, will be uniquely solvable for a velocity pressure pair if and only if the data live in an appropriate regularity class, which I won't tell you explicitly, but it's completely standard. And they satisfy the two compatibility conditions that I mentioned before, namely this integral condition is satisfied, and we have inclusion in the Sobolev space h dot -1 for this sort of weird function determined by h and g. And moreover, not only do we have a sort of PDE solvability result, but this induces an isomorphism between this standard Sobolev space and the space Z that that encodes this regularity as well as the two compatibility conditions. I don't want to tell you precisely what it is, but it's some nice Banach space that we can write down. So, okay, this is great. By sort of bashing this with compatibility conditions, we're able to sort of exactly characterize when we can solve the overdetermined problem. What we would like to do is to go back to our original problem involving eta, but first it turns out that it's convenient to get rid of this formulation of the problem because this has this sort of free function phi floating around in it, and it's kind of convenient to remove that. And so to do that, what we're going to do is just notice that we can reformulate this condition by applying the horizontal Fourier transform, and then using this to deduce a pointwise condition that has to be satisfied for the horizontal Fourier transform. So we can find an equivalent formulation, which I've written here on the Fourier side, where now this function v and this function q are special functions that essentially correspond to the Fourier transform of the Green's function for the the special isomorphism that I was talking about before, the one that we use here to parameterize the kernel of the underdetermined problem. So, whoops, I've gone too far. So these are things that in principle we can explicitly solve and compute on the Fourier side. They're solutions to some nasty ODE. Okay, so this is now a pointwise condition. What's nice about this is now that it's a pointwise condition, I can return to my original problem and say, okay, if I have a solution UP eta for the original, the traveling wave version of the Stokes problem, then necessarily I can think of eta as being part of the forcing terms here, and I will have to have that the compatibility conditions are satisfied. And so for this problem, I will find that the compatibility conditions have to be satisfied by F, which hasn't changed, G, which is the same, and then I'll move the eta term onto the right and view it as part of the H term, and K I'll move onto the right, sorry, this term right here, I'll move onto the right and view as part of K. So I now have necessary and sufficient conditions on F, G, this thing, and this thing in order for a solution to this problem to exist. Let me ignore for now the first compatibility condition. It turns out to not be a problem. The second compatibility condition, though, actually is a rather seriously interesting thing here. So what we're going to do is we'll plug into our integral condition that, or our pointwise condition rather, for the second compatibility condition. If you plug into that and rearrange, what you actually get is an explicit equation that allows you in principle to compute the Fourier transform of the free surface function in terms of the rest of the data. And in fact, what we find is that on the Fourier side, there's a Fourier multiplier that obviously multiplies the free surface function on the Fourier side that has to be equal to a fixed function psi that can be computed explicitly in terms of the data. And our multiplier is something that is almost explicit. So it's our Fourier multiplier, which will induce a pseudo-differential operator, rho. Its symbol is the combination of three things. So it's this part here, which is coming from the traveling wave part. It's this part here, which is coming from the gravity capillary operator. And this function V in, which I mentioned previously. So let me focus on, if I want to understand this problem, obviously I'm going to need to be able to compute eta by dividing by rho here. So I really need to understand the behavior of rho as xc goes to 0 and as xc goes to infinity. And that's entirely going to boil down to my ability to understand V sub n. So let's focus on that a little more carefully here. It turns out that this function V sub n that I'm writing down here, it's actually the symbol associated to a nice pseudo-differential operator. And what it does is it takes a function phi, which is an HS of the upper boundary, and it maps it to a function that is an HS plus 1, also on the upper boundary. And that function that it maps to is the normal component of a velocity field traced onto the top, where that velocity is associated to a solution pair UP to the Stokes system with applied stress conditions that we saw before. So the idea basically is I take a function phi, I use it to solve the applied stress Stokes problem here, and then I take the corresponding velocity field and I take its normal trace onto the upper boundary. So this is what we call a normal stress to normal Dirichlet map, because it's a sort of vectorial Stokes analog of the Neumann to Dirichlet map, which is the inverse of the usual Dirichlet to Neumann map that we encounter frequently in free boundary problems. So what that means then is in our operator rho, we have a pseudo-differential operator that is going to determine the free surface function in terms of the data. And remarkably, it synthesizes all three of the operators that act on the free surface function. It synthesizes the traveling wave operator, the gravity capillary operator, and the normal stress to normal Dirichlet operator. They all come together to determine this single pseudo-differential operator that we need to invert in order to solve for the free surface function. Let's see here. So it's 9:50. Am I out of time, Stanley, or should I? Can I have?
I think you can go for a few more minutes. It's okay.
Okay, cool. Thank you. Okay, so I will cut this short, but let me at least get to the crux of the next point here. So again, we're trying to solve on the Fourier side. The identity rho times eta hat is equal to this function psi that is constructed in terms of the data. So in order to solve this, I basically need to understand the behavior of rho. Now, we can get our hands on this through a very lengthy set of calculations where we sort of basically explicitly solve the ODEs that correspond to V on the Fourier side. And what we find after a bunch of work is that, in fact, rho does vanish at the origin, but that is the only place where it vanishes. So we have the problem where our symbol vanishes at the origin. So there's going to be some issues at low frequency here. And moreover, we can compute the asymptotics of rho. And in particular, we find that rho squared has sort of very different behavior depending on the dimension and depending on whether we have surface tension or not. So in dimension 3, as long as surface tension is positive, then for high frequencies, we find that this behaves like a standard multiplier corresponding to a derivative. At low frequencies, it has this strange anisotropic behavior where we see the free surface speed multiplying just c1, which is just the direction associated with the direction of propagation of the traveling wave, and then there's a higher order term c to the fourth. On the other hand, when sigma is 0 and the dimension is 2, what we find is that, so xc1 is actually just xc in this case, because when I say n is equal to 2, that's the dimension of the ambient space. So the dimension then of the cross section is 1, and that means that xc1 is the entirety of xc. So I get much better control when the dimension is 2. And I also get similar control at high frequencies by employing the gamma part of the equation. And essentially what's really going on here is that when I'm in dimension 2, the cross-section is one-dimensional, and this traveling wave operator is an elliptic operator in one dimension. So I can use that to get sort of elliptic control at both low frequencies and high frequencies when I'm in dimension 1. Okay, so somehow the point is the symbol is much nicer when we're in dimension 2, and it's so nice, in fact, that we can set sigma to be 0 there and still have the same level of control that we got with sigma positive. Okay, so let's be a little more specific about this. In dimension 3, using these estimates, it turns out that the absolute best that we can get is what we get by taking this equation and also dividing it by the absolute value of xc. And the reason for that is because somehow at low frequencies, our function psi lives in the space h dot minus 1. And this has to do with the first compatibility condition. So what I've recorded here is the absolute sharp estimates that we can get for our free surface function based on the compatibility conditions and the regularity conditions on the free surface function. So this is really the best that we can get here. And notice that there is a significant difference between the case 3 and 2. At high frequencies, we don't really see a difference. We just have standard Sobolev control of the high frequency parts of both. This looks just like an HS plus 5/2 norm for both of these things at high frequencies. But there is a major distinction that happens when we go to low frequencies. When I'm at low frequencies and I'm in dimension 2, then actually I'm still going to get something that looks exactly like standard Sobolev control. So this will in particular control the L2 part at low frequencies, or equivalently the HS part for any S. And as a result, what that means then is when we're in dimension 2, we can get standard Sobolev control of our function. However, of our free surface function. However, when we're in dimension 3, our low frequency multiplier is this weird anisotropic thing. And this is not going to give us standard Sobolev control at all. It's going to give us better control sort of in the C1 direction and worse control as we move to, let's say, the C2 direction. So there's definitely an anisotropy that is implicit in this thing here. Okay, so what this is telling us is that necessarily, if I can construct a solution to my problem, then the estimate that I'm going to get for my free surface function is not necessarily going to be in a standard Sobolev space because of this condition here, at least in dimension 3. And what this suggests is we say, well, look, this is what the problem gives us. Let's work with it. So we're going to define a special scale of Sobolev spaces, at least for use in dimension 3 and higher, that exactly capture this behavior on the Fourier side. And this is where a technical miracle happens. So when we do this, we end up with something that actually is a nice Hilbert space. It's complete and has all sorts of nice functional properties. But what's most important is that if I look at 1 over this multiplier that I'm using on the Fourier side, this actually is integrable. And what that is going to allow me to deduce via a simple Cauchy-Schwarz argument is that the low frequency part of the functions in this space is going to be are going to be an L1. So what that means is all of the elements in this space XS can be decomposed as a band limited function that's in the Wiener algebra, plus something that is in that's not band limited, that corresponds to the high frequency stuff and is in a standard Sobolev space. So these basically are going to be good objects to work with from a PDE point of view, because we can get pointwise control by going supercritical, at least in the value of S. What's weird about this space is the anisotropy of this symbol leads to a strong anisotropy in the space itself. So we can find functions that are in this space such that if I compose them with a 90-degree rotation, they leave the space. So there's a strong sort of bias to the direction of motion for the traveling wave. Also, these things have good embedding properties and excellent nonlinear functional analytic properties, which is a necessary condition to use these things in the context of the implicit function theorem. Okay, and I'm gonna jump ahead here and just say, once we identified these spaces as the right objects to work with, we were then able to prove that our full traveling gravity capillary problem for the Stokes system actually induces an isomorphism as long as we work in some strange spaces. So I'm not going to tell you what the space YS is here. It's another weird space, but I'll commit the sin of jumping past this. So the moral of the story is we then have our isomorphism. We can then go back and set up our original nonlinear problem in the flattened coordinate system as an implicit function theorem argument. It turns out then with a decent amount of work, we can prove that all of the hypotheses of the implicit function theorem are satisfied, and we can then hit this thing with the implicit function theorem and produce solutions in order to solve our problem. The one thing I want to mention from this slide is just this. All of this is then producing solutions in the flattened coordinate system. And of course, then the question is, well, can we go back to the original system? And the answer is yes. The estimates that we're able to prove for the free surface function are nice enough that we can sort of recompose with the inverse of the flattening map and go back to the original coordinate system. So we can sort of unflatten and produce solutions to the original problem. Okay, and I'm sorry to run over. Let me thank you for coming today.
All right, let's thank Ian, either verbally or with those reaction emojis. Or I guess this is one aspect of Zoom talks we haven't really figured out yet. But yeah, in any case, let's open the floor for questions. Oh, before we do that though, there was a mistake in the chat message that I shared earlier in the talk. Yeah, so I just copy pasted the one from last week. It says there's a related journal article. So there is no related PDEA journal article for this talk, so just ignore that link. Sorry about that, whoever was confused. In any case, yeah, let's open the floor for questions. Maybe while people are formulating their questions, I'll ask one of mine. So I guess when the width of the channel or the slab gets smaller, then I guess you would be in a shallow water waves situation, and then I suppose it would be more of something you'd model with KDV, as I understand. So I don't know if there is any sort of correspondence between, because I know people also study traveling waves for KDV. Is there any correspondence or anything interesting to say about the sort of either the relationship between the two regimes or somehow taking some formal limit from one to the other?
Yeah, absolutely. So, yeah, so I mean, this is, I'll give you the typical, sort of analyst answer here, I guess, that, like once we have existence of solutions, this opens the door to answer, to asking and answering more sophisticated questions like, can we actually pass to the limit as either? So, there are lots of things to do here, not just consider the limit as, let's say, the thickness goes to 0, There's also the thickness going to infinity, which is the so-called infinite depth regime. There's also the natural question of what happens if, for instance, the viscosity goes to zero. Once we have our foot in the door, yes, all of these are perfectly valid questions. So I will, let's say, remain agnostic as to what the results might actually be. So I have no idea if you know the solutions that we're able to construct will be let's say will come equipped with estimates that are strong enough to actually accomplish this limiting process. It's possible, but I don't know is probably the safest thing to tell you. But yeah, absolutely. So you are right that in the shallow water regime, there are lots and lots of models that are meant to handle the various scenarios that can arise. Because there are also things that you need to take into account, like are your waves going to be essentially of high frequency or low frequency, and I think everything has to be dealt with in terms of the depth parameter, right? So I'm not an expert in the various limits that you can get through this, so I might be I would probably misspeak if I said, oh, I suspect we will get this version of some dispersive model. It will presumably depend on the scaling of the different parameters and the scaling of the forcing, etc. But the thing that I would like to emphasize is that this is the beginning of the story, in the sense that now that we have the existence of these things, we can then begin to attack their qualitative properties.
Yeah, well, and I guess also existence of the dynamic problem. I was also curious about whether there's a sort of, for example, if you want to look at stability of these traveling waves, then it seems like it would be a whole hard story even just to construct time-dependent solutions to the true system.
That is absolutely the next thing in the pipeline for me. And you're absolutely right. This is the most natural question you can ask, because we've constructed these things, but if they're dynamically unstable and you never view them in nature, of course, there's always the response that a physicist would have of saying, okay, well, who cares? Why did you why did you build these things if they're not there? The response that I would have is, the starting point was some experiments that we saw that actually seems to indicate these things are there. So I do think probably we will be able to prove a dynamical stability result going forward. Do we have it in preprint form yet? No, not at all.
All right. Other questions?
What happened with the zero speed case? You talked about at the beginning a problem with when the speed of the traveling wave was zero versus non-zero.
Yeah. So I can tell you exactly by pointing at this slide. So what goes wrong is if I set gamma to be zero, then the estimate that I get from doing this analysis just deletes this term right here. And what I will get is control of my free surface, the low frequency part of the free surface. Basically, I get control of it on the Fourier side with the multiplier just c squared here. And unfortunately, because of the dimension, this is not enough for me to guarantee that when I hit this with the inverse Fourier transform, I get a nice function. So the problem is that h1 dot in 2 dimensions is critical, and so I get essentially minimally useful control out of this when gamma is equal to 0. So this is the weird sort of thing about this problem is the traveling wave stuff causes all sorts of problems. The appearance of the gamma terms cause certain annoyances when we're doing the analysis, but at the end of the day, those terms are also 100% responsible for allowing us to actually produce the solutions, because they provide just a tiny little bit of extra control that is enough for this technical miracle to occur, for us to actually guarantee that the things that we get are functions.
Thank you.
Yeah, sure. My pleasure.
Other questions or comments? All right, if not, then let's thank Ian again for that very interesting talk. Yeah, and then let's hope everybody joins us next week. We've got Christian Kuhn speaking about geometric singular perturbation theory for fast slow PDEs. Otherwise, yeah, thanks everyone for coming, and everybody have a good day.